Section 13.1, Intro to Functions of Several Variables. So in this section, we're going to be talking about functions, not just y as a function of x, but now we're going to be talking about functions like z as a function of x and y, or w as a function of z, x, and y, right? So these are things that are going to depend on several variables. So a good example of this would be something like a volume. So consider the volume of a regular cylinder. All right, that is given by V is equal to pi r squared h, where r is the radius of the cylinder and h is the height of the cylinder. Okay, so the variables here are both r and h, right? So V is a function of r and h. Or we could write that as V of RH. Okay, so that's kind of how we're going to be looking at these things. Now, typically, we are going to have z defined as a function of x and y. So where so z is equal to f of x, y, where x and y are the independent variables. And z is, of course, the dependent variable dependent on both x and y. So anytime we're discussing functions, we have to discuss the domains of those functions. All right, so recall that domain restrictions can occur in three specific instances. And this is a maybe situation. It's not an absolute, just it could happen. So first, it can happen if we have rational functions where variables are in the denominator. It can happen if we have radicals, so any kind of square root, even root. Odd roots don't count, of course, because we can take the odd root of a negative number, but we cannot for even numbers, for even roots. And then finally, the logs. If we have a log, of course, we have to make sure its argument is greater than 0. Okay, so in the first instance, we cannot allow denominator to be equal 0. Okay, so we can find restrictions on the domain by setting the denominator equal to 0, finding those values and excluding them from our domain. For radical functions, the radicand must be greater than 0. Greater than or equal to 0. So we can take the insides of our radical function, that's the radicand, take that, set that greater than or equal to 0, and what we're left with is the domain for our function. Fix radicand there. Yeah, that's better. And for logs, the argument must be strictly positive. We cannot take the log of a negative number or of 0. So our logs must be strictly positive. So the argument, not the log, the argument of the log must be strictly greater than 0. All right, so let's do an example where we have to find the domain of a function. All right, so we have f of x, y is equal to 1 over x plus y. Okay, so this is a rational function. We have variables in the denominator, so we're going to set that denominator equal to 0 and exclude those values from our domain. So we cannot have x plus y equal to 0. Okay, so in that case, as I said, we're going to set it equal to 0 to find what our values cannot be. We cannot have x equal to negative y. So then the domain for our function, f, is going to be the set of all xy such that x is not equal to negative y. And there are several ways that we can describe this. We can say, all real numbers x and y such that x plus y is not 0, all real numbers x and y such that x is not equal to negative y. There are several different ways we can describe this, but the important thing is that we are cognizant of anything that would cause a singularity in our function, so any place where it would not exist, where it would not be defined. So let's do another one. So let's find the domain for g of xy equal to the square root of x squared plus y squared plus 4 divided by the square root of 4 minus x squared minus y squared. Okay, so we have got square roots in the numerator and denominator. So we've got a lot of things going on here. First, it's a rational function where we have x and y in the denominator. So we have to make sure that our denominator is not equal to 0. We have square roots, so that's even roots. We have to make sure that nothing inside of those can come out negative. We can only have zeros or greater inside of a square root. So the first thing I want to do is I want you to notice that the numerator, x squared plus y squared plus 4, being inside of a square root must be greater than or equal to 0, which means x squared plus y squared must be greater than or equal to negative 4. But x squared plus y squared is always positive because we're working with real numbers. So this is always true. So x squared plus y squared is always greater than or equal to negative 4. That means that there are no restrictions on our domain coming from the numerator. These are always going to be valid no matter what x and y we pick. So no restrictions here, okay? Now, the next one is our denominator, because it's inside of a square root, must be greater than 0, greater than or equal to 0. And because it is in the denominator, it cannot be equal to 0. So from our denominator, we have 4 minus x squared minus y squared strictly greater than 0. So it has to be strict because it's in the denominator. Okay, so then we can work with this a little bit, and what we find is that x squared plus y squared must be less than 4. And that's the relationship for our domain. So since there were no additional restrictions from the numerator, our domain for g is simply going to be the set of all xy such that x squared plus y squared is less than 4. Okay. And there are many ways that we can describe this. One thing we want to be careful to do is not to say, well, x is a number between negative 2 and 2, and y is a number between negative 2 and 2. This would actually generate a square, and x squared plus y squared equal to 4 is a circle of radius 2, right? So we want to be really careful about how we define these things, and this relationship is in place because as x increases, y will decrease, as x decreases, y will increase, and there's going to be that power play between them. So there's always this relationship between the two as we are coming up with our domains. So you might have noticed that this g function contains x squared plus y squared in a couple of different places. We could have reparameterized this. So this is not a necessary step, but it's something that if you notice it, you can do it. So we could reparameterize g, okay, because r squared is x squared plus y squared. So then g of xy would be equal to g of r, which would be equal to the square root of r squared plus 4 divided by the square root of 4 minus r squared. All right, and we would set it up in much the same way. R squared plus 4 must be greater than or equal to 0, which is always true. So no additional restrictions here. And then 4 minus r squared must be strictly greater than 0, which means r squared is less than 4, which means r is between 2 and negative 2. So we could set this domain up as r such that r is between 2 and negative 2. And it's not including the 2's because that would make a 0 in our denominator. But this is a secondary way that we could have set this up. Okay, so let's go back and now let's talk about the range of g. Okay, so the range of g of xy equal to square root of x squared plus y squared plus 4 divided by the square root of 4 minus x squared minus y squared. So what is the range? Well, the range is the set of all z that can be output by this function. Okay, because we have z is equal to this function of xy. So we need to start analyzing this and see what can happen. What can happen in my numerator, what can happen in my denominator. So remember, x and y are the set of any numbers such that x squared plus y squared is less than 4. Okay, so we're working, let's think about this. X squared plus y squared equal to 4, that's the circle of radius 2. So if we're just looking in the xy plane, that's what we're looking at right there. X squared plus y squared is equal to 4. So now we're looking at the z component of this, and we want to know what is this going to do to our function. Well, first of all, we know that our denominator is some number between what and what. So our denominator is between 0 and 4, including the 4. Right? So if x and y are 0, 0, our denominator, not 4, 2, the square root of 4. I'll just go ahead and correct that. Okay, so it can actually be equal to 2, but we can't allow it to be equal to 0. Okay, so that's our denominator, and our numerator can be as small as square root of 4, or 2, because xy, if xy are 0, 0, then we'll get that. But then, as x and y get larger, it's going to grow. So whether x and y get larger or get smaller and become more and more negative, that numerator is going to grow and grow and grow. So the numerator can be as small as 2 and will increase without bound. Okay. Okay, so if we divide by a number smaller than 1, we're really just increasing the value. Okay, and if my numerator is growing without bound, that means we have no upper limit, or it's just going to continue to increase. So then we've got to deal with this denominator and how small the numerator can get. So the numerator can go all the way down to 2. That's as low as the numerator can go. The biggest the denominator can get is also 2. So the smallest denominator is 2. I'm sorry, numerator. Just said that. Smallest numerator is 2. The largest denominator is 2. So the smallest our function can be is the smallest denominator over the largest smallest numerator over largest denominator. So that would be 2 over 2, which is 1. So that's as small as it can get, and it's going to increase without bound. So the range for this function is going to be 1 to infinity. Okay. So that's going to be the range for this function. If it's in set notation, if you prefer that, we could set that up this way. It's z such that, I guess to be technical, z is a real number. I haven't been picky about that up to this point, have I? So z is a real number such that z is greater than or equal to 1. That's going to be the range for this function. So either way you like to set this. In the homework, it's just going to be asking you to describe it. It's not going to be asking you to put it in any crazy notation. But I think it's important that you see this. All right, so now let's talk a little bit about sketching these and how we're going to do that. So we're going to use something called level curves or contour curves to sketch these. Okay, so a level curve is really just a trace in a plane where z is constant. So a level curve is a trace of a surface in a plane parallel to the xy coordinate plane. In other words, where z is constant. Okay, so that's what we're going to do. We're going to find the trace for this function given a constant z, and then we're going to sketch that. So you might have seen a contour map of a mountainous region or something. So let's take a quick look at a contour map just to kind of help you see what's going on here. If you have a map with a bunch of mountains, so let's say you've got a bunch of mountains on your map, you'll see on the map itself, you'll see a whole lot of concentric curves, right? And they don't necessarily have to be circles. They could be, something that gets a little more out like that, and maybe it comes out a little further like that. And what these are doing is each one of these curves is representing some elevation. So remember, my map was showing me some mountain, so some mountainous region. And each curve is representing some height, okay? So each curve represents some height. Okay, so maybe this height in the very center here is 10,000 feet. And maybe the next height would be 9,000 feet. And the next height would be 8,000 feet. Whatever it is that we choose, we want our curves to be incremental. We want them to be at increment levels of z. So we select our levels, in other words, the constants for z, at incremental levels. Okay, so on this map, maybe I'm choosing increments of 1,000 feet. On a sketch that I'm drawing, maybe I choose my increments at 1, like 1 integer, 1 whole unit. I could choose it by 2 units. We could choose in any units we want. We just want to keep it consistent. So it's not likely that we would choose our constant z levels to be 1, 10, 150, 1375. We probably wouldn't choose them that way. We want it to be fairly consistent. And the reason for that is because the closer together the curves are, the faster the grade is increasing. So the closer the curves are, the steeper the increase between them, increase or decrease. Okay, and we're going to talk about how to find that increase and decrease in each direction, x, y direction. We're going to find that later, and then we're going to talk about something called the gradient, which kind of gives you an idea of the steepness of your slope wherever you happen to be standing. So if you're standing on a mountain, we can think about the different, if I move in this direction, how much will I be increasing going in the x direction, y direction, right? So we can think about all of those things. So we're going to get to all of that. For now, let's go back to just focusing on how do we create this sketch of level curves, okay? So here's what we do. So level curves are sketched in the xy plane. Okay, we begin by choosing our constant values for z. And we'll choose several of them. We'll have z equal to c1, z equal to c2, z equal to c3, z equal to c4, etc. Okay, so we'll just continue this. So C1 is our first constant, C2 is our second constant, C3 is our third constant, etc. And we want these to be with, in some kind of incremental steps. So increasing by 1, increasing by 2, by 5, 10, whatever we choose, but it needs to be incremental. Then we substitute each number in for z. Okay, then we sketch the resulting curve. Then we label each curve with its constant. Label each curve with c sub 1 equal, well, say c sub I equal to whatever that constant is, right? So whatever constant that's equal to. And that's how we're going to sketch these. So let's go ahead and do an example. Let's have f of xy equal to the square root of 4 minus x squared minus y squared. Okay, so we're just going to do that. Now, first of all, we already know the domain of this. Well, it's slightly different because we can include the 0 now. So the domain for our function f is going to be all xy such that x squared plus y squared is less than or equal to 4. Okay. Then our range for this function, it's going to top out at 4, right? Because we are subtracting x squared plus y squared. Now, x squared plus y squared is always positive or 0. So the smallest x squared plus y squared can be is 0, which means we would end up with the square root of 4. The biggest x squared plus y squared can be is 4, because we can't go past that or we violate the domain. So the smallest my function f can be is 0. So my function value z for z is going to be between 0 and 2 the square root of 4. Okay. All right. So we've got, we have our range, we have our domain. So my z's are not going to be greater than 2, and they're not going to be less than 0. So we will choose our c's. Let's do that. So I'm going to choose c1 equal to 0, I'll choose c2 equal to 1, and I'll choose c2 equal to 2, just to keep it simple for this example. We could go in half units if we wanted. We could have 0, 1 half, 1, 3 halves, 2. You can break it down further if you like. It's entirely up to you. Or the instructions given by the question, right? That might be something we have to watch out for. Anyway, so we want to go ahead and sketch this. So I'm going to go ahead and sketch the level curves. So I'm going to do this. This is the xy plane. So I'm going to give it a pretty big scale here. Okay, and then we're going to begin. So I'm going to choose a different color for each of my curves. You do not have to do this, but I'm going to do that just so that hopefully it's easier to see. So for c1 equal to 0, okay, that means z, which is f of xy, z is equal to 0. So I have 0 is equal to the square root of 4 minus x squared minus y squared. So if I solve this, I get x squared plus y squared is equal to 4. That's a circle of radius 2, so we can sketch that. Okay, so bear with my poor art skills here again. There we have C1, which was equal to 0. So that's my first level curve. So when z is 0, in other words, when I'm on the xy plane, the trace of my surface is a circle of radius 2 centered at the origin. All right, so let's now go to the next c. So we have c2, which is equal to 1. So that means I've got 1 equal to the square root of 4 minus x squared plus y squared, which means x squared plus y squared is equal to 3. All right, so that's the circle of radius root 3, which is approximately 1.7 or so. So at about 1.7, it's maybe right about here-ish. Okay, so that's going to be the radius of our next curve. So if I were to, oops, come around here like this. Yeah, beautiful. Okay. So that's my next curve. Now, please remember, these are supposed to be circles, and I recognize that I'm not good at drawing circles. C2 is when we have z equal to 1. So if I were to go up to the plane, so just lift straight off of the xy plane, straight up into the air here. If I were to lift straight off of that up to z equal to 1, the trace for my surface in that plane would be this circle of radius root 3. Okay, so let's get another color and let's do our last one, C3. Oops, check it out up here. I wrote C2 twice. I've got C1, C2. This should be C3. This is our third C. That's all that index means. We're just counting. All right, so I've got C3. is equal to 2, which means 2 is equal to the square root of 4 minus x squared plus y squared. Square both sides and solve. I get x squared plus y squared is equal to 0. 2 squared give me 4. Subtract, I get 0. So that is just 0. So x squared plus y squared equal to 0. So that's going to be the circle of radius nothing, which is just going to be the point here. So just 0, 0 is the only value we have that will satisfy that. So this is C3 equal to 0. Okay. Now, what has this done? This has shown me where is my curve from in the xy plane, 1 step above the xy plane, and then 2 steps above the xy plane. So if we were to take this and try to sketch this out onto a 3-dimensional space to the best of our abilities, this is y, z, and of course x. This is what we're seeing. So let me mark this off. We've got 1, 2, 1, 2. Little perspective, trying to keep that closer together on the x-axis. Really do need to go in this direction as well, I suppose. 1, 2, and 1, 2. There we go. Okay. Whenever z is equal to 0, what we found was we had a circle of radius 2. So we had our trace was the circle of radius 2. Okay. Then at z equal to 1, we had a circle of radius root 3. So we come up a little bit here. So it looks like we would have circles about here-ish. Okay, so this is our next circle happening here. Oh man, this is painful, painful to watch. Okay, and then finally, at the very tip top of this, we just have the single point where z is 2. We have x, y. And so hopefully you can see what's happening here. We're getting this dome, this half sphere. So we have our half sphere here kind of coming through. And yeah, so what we did up above was we drew these level curves, so these circles within. So the trace for that plane where z is equal to 1, the trace where z is equal to 2 is just the point, and the trace where z was equal to 0 was the circle in the xy plane of radius 2. So hopefully that helps you see this. I know it's really hard to do that whenever you're just looking at it in 2 dimensions, especially with drawing in this way. But your book has some wonderful illustrations. Khan Academy has some great videos. OpenStax has some great resources. So I highly recommend that you check those out if you need a little bit of extra help seeing these contour lines and how they relate to the actual surface in 3 dimensions. All right, and one more word on multivariable functions before we move on. Multivariable functions are going to behave in exactly the same way as single variable functions do. Okay, so multivariable functions, let's say properties of multivariable functions. Okay, so for f of x, y, and g of xy, which are multivariable functions, we have f plus or minus g of xy is equal to f of xy plus or minus g of xy. Okay, we have f times g of xy is just f of xy times g of xy. We have f divided by g of xy equal to f of xy divided by g of xy, provided, of course, g of xy is not equal to 0. All right, and then composing works again in a very similar method. So here we have to change this up a little bit. Let me just write that down. Composition of multivariable functions. Okay, so given that f is a single variable function, So if we have a function f of x and g is a multivariable function, g of xy, then f composed with g of xy is equal to f of g of xy. Okay, so again, we have to remember, in this instance, f is a single variable. F is a single variable function. Okay. If f were a multivariable function, the composition would have to be defined in a completely different way, because what function are we putting in where, which variable is getting replaced with what, that kind of thing. So we're not going to work with that. We're just going to work with this. Okay, so if you have any questions about any of these things, please do let me know. I wanted to make sure that you were aware that the multivariable functions, their behavior is just like that of single variable functions as far as combining those functions goes. Sketching these is much easier, I feel, than sketching in 3 dimensions, because we're just looking at our XY plane, which is something we've been looking at for years and years, right? So we're very comfortable with that. And it's intended to help us get a picture of what's going on as we move forward into the 3-dimensional space. And we're going to see a lot more with contour lines and kind of how we can interpret those, how we can see that affects various components of the surface. Where is it increasing the most? When is it, where is it decreasing? That kind of thing. So more to come on that. But as always, if you have any questions, please let me know.